That's not working. There we go. So I do want to bring one thing to your attention before we get started. The ACM is a national organization called the Association for Computing Machinery. It's the professional organization of computer scientists in the United States and abroad. It's the largest computing association in the world. We have a student chapter here. The student chapter is made by students like you, from freshmen to seniors and even a few graduate students. They have a club, we provide pizza, they do stuff. That's sort of the equation. And they're having their first meeting of the term on Monday, so I'll advertise ACM activities here. And if you're free, you want to meet other CS students, informatics students, data science students, CS&E students, this is one way to do it. They're hosting a conference the last weekend in February is our traditional day. It's going to be an online conference this year, but it will have some in-person social activities. So I'll advertise that as the time draws nearer. But if you want to get a head start, you're all invited. You probably just got an email about it today as well. Okay, so let's get back to where we were. By now you should have read the syllabus. Any questions about the syllabus? I'm sorry for the mess up on the midterm exam dates. I said there were 3 midterms. I gave you 2 dates, both of them wrong. I have some tentative dates in mind, but I want to place it at the right point. So we'll talk about dates for the midterms as they get closer. But roughly speaking, I'll give you a sense of when they'll be. I'll post it to the website today. You've all found the ICON website, I take it? And you'll notice I post after every lecture. I post sort of any announcements on the front page, on the landing page. And they'll be sorted in reverse order, so the newest things will always be on top. And if you click on the lecture index, you'll find that there's a summary of every day's lecture after the lecture's over. You'll see the titles of the things we did in the lecture. And that's also posted, the newest one first. So you have an idea of, if you want to go back and figure out which lecture to look at, you can skim the index, and then you go to UI Capture and you can watch the lecture. Did anybody pull up the recording of the last lecture? Yeah, so I apologize for starting it late. I forgot. I didn't forget today, so we should have all the recordings from now on. Ah, nuts. Okay, you should have read Think Python Chapter 1 and Python for Everyone Chapter 1. There was a question on Piazza. Good for you for those of you who managed to post or read Piazza. This is the shorthand for Think Python. That's the shorthand for Python for Everyone. They're both drawn from the same open source text, but they're a little bit different. So sometimes I'll assign readings from both. Sometimes I'll assign from one or the other. So pay attention to what it says on the and or the or. On Monday, sometime in the afternoon, I'll post the instructions for Lab 0, which is a non-credit lab. It's installing Python on your machine. There will be instructions there. My plan is that on Tuesday in your discussion sections, you'll be able to go over and get help if you got stuck doing this. And TAs will model for you how to install ICON on your laptop, or Python on your laptop. From now on, after Tuesday's discussion section, we'll be doing in-class labs. But next Tuesday, the first lab section, will be sort of a kind of a tech support lab to get you so you have stuff working on your machine. All right, and thanks for those of you who went to Piazza. That's where you should go first. We try very hard to answer those questions quickly. So if you want help or you have questions, that's the place to do it. You can post anonymously. That means you can ask any question you like within reason, and nobody's going to say that was a really dumb question, because nobody knows who you are except for me. I do know who you are, so don't say nasty things about the instructor. I'll know who you are. Finally, if you do email, make sure you put CS1210 in the subject line. I have 13,800 unread messages in my inbox, and they accumulate at a very rapid rate. Unfortunately, a lot of stuff I get is spam, but I can't filter it out because stuff gets lost. So I try to triage best I can, but I'm hopelessly behind with email. Piazza is a little more tractable. And apparently nobody's had trouble with ICON or the videos. Okay, so let's pick up where we left off. We're talking about what a program is, and I gave us sort of a short definition. So let's review what that is. A program basically reads in some data, does some calculation, which we haven't defined yet, and it always produces the right output in a finite amount of time. There's a lot of loaded things in that statement, so let's see what they are one at a time. So a program is correct, meaning that it produces the right output if it meets the problem specification. In other words, I ask you to solve the problem of adding some numbers together, and you write a program that subtracts numbers from each other, it's not going to be correct. There's nothing wrong with the program, it's just not what I asked you for. So matching the specification is how we know that a program is correct. And that begs the question of what the specification looks like, and it's usually expressed as a mapping of, if I get this input, this is the output I want. Now we can do that mapping in a lot of ways. We could give you a table and say, for this input, give me that output. Or we could say, for inputs of this type, give me the output calculated in this way. And so on and so forth. So this mapping is a little vague for now, but we'll see an example in a second. The program you write should always terminate, meaning it should always run in a finite amount of time. You can write the world's best computer program that solves the world's hardest problem the best way possible, but if it never returns, if it never ends, it's not going to do anybody any good. So finite time termination is important, and when it terminates, it should produce that correct output. Now the philosophical problems we have are that determining termination can be difficult. In fact, it's actually provably impossible to guarantee that your program will terminate on all possible inputs. Now that's not exactly true. It's possible to do it for a specific program sometimes, but for programs in general, there's actually a proof of a problem called the halting problem, which we'll discuss at the end of the semester, that shows you that it is impossible to write a program that determines if a program will halt. And that's kind of a philosophical twist to the problem of writing programs. And finally, it's hard to know if a program is correct because correctness depends on having the right answer for every possible set of inputs. And inputs can be infinitely large. Input sets can be infinitely large. In other words, if I say, write a program that predicts the GPA of every student at the University of Iowa, that's maybe tractable because there's 25,000 students. But if I said, write a program that predicts a GPA for every possible student in the world in every possible future year, and we have essentially an infinite set of possible students, it's hard to prove that that program is going to be correct. And you certainly can't test every possible input because you don't even know what they are. So this is where we are, and I promised you we'd do this. We talk about what CS people do, and we'd solve a problem today. So we're going to introduce the problem, we're going to solve it. I'd ask you to think about it before class, and I'll get your input in just a second. So here's what a CS person does. You start with a problem specification, which we often have to sort of clean up, because we want it to be rigorous enough so that we know what we're writing the program to solve. Secondly, we derive this strategy or an algorithm or a mechanism by which we can solve the problem that we're asked to solve. We make some argument about this algorithm will always terminate, or this algorithm will always produce the right output for this particular set of inputs, and so on, best we can, when it's possible, as we just discussed. And once we're sure that everything is right and as good as we can do, only then do we sit down and write the code that implements that algorithm. So here's the sort of the big picture for today. A lot of CS1 students, this is where you start. And that's not where you should start. Think first, program second. So when you get an assignment, don't just immediately sit at the programmer and try to hack something together. It's not a successful strategy. Think about it first, program second. And then finally, when you have the program done, you often select a representative set of inputs to test your program to make sure that, not that the algorithm is correct, because presumably you've already done that, but you test your program to make sure that your implementation is correct, that you didn't mess things up along the way. So the picture for today's problem, which I introduced, is the stable marriage problem. And now I'm going to talk about the specification of this problem. So the idea is, the general idea is that I have a set of of men and a set of women, and they're like-size sets, same size of number of people. And what I want to find is called a matching, or a pairing of one man to one woman. I need to do that for every possible person. So in other words, in this case, 5 marriages or 5 pairings that meet some particular specified objective. See what that is. So we're going to start by cleaning up my problem specification for this problem, which was very loosey-goosey just now. I want to make it formal. Then we're going to talk about a design of an algorithm to solve the problem. We're actually not going to do the implementation today, but you'll see the implementation later in the term. That implementation takes my problem sort of approach, my algorithm, and produces a program in Python or in C or in Ruby or whatever language I choose to work in. And then that program, which the programmer writes, will be compiled or interpreted to produce another version of that program in a different language, a language that's specific to the device you're running it on. So I may write the program for my Linux desktop or my Linux server or a Windows machine or my Android phone, and the machine code will be different in all those cases, but the program will be written in the same language, Python, C, Ruby, whatever you like. Okay, so that's the big picture. Let's get back to our problem specification. So, stable marriage problem says match n men and n women such that no man and no woman matched to another would prefer to be matched to each other. So remember that picture of the 5 men and 5 women? We're going to pair them off such that if I have a marriage between a man and a woman and another marriage between another man and another woman, there is nobody who would prefer that pairing to be inverted. Right? So that's what we mean by stable marriage. You imagine all these marriages, you throw them in the same room, people get to know each other and say, hey, we're going to swap. We'll all be happier if we swap. We don't want that situation. All right? Now, unfortunately, computer scientists have a lot of quirks. I'll tell you 2 of our quirks. We love colorful names for our problems. So the stable marriage problem is a colorful name for a problem that has a lot of incarnations. Nobody wants to call it the stable matching problem or the stable pairing problem. They call it the stable marriage problem because it makes introducing it to students much more intuitive. It's a little anachronistic, it's a little paternalistic, but there you have it. And it's hard to change some of these names now. So just sort of bear with me with the name of the problem. The second quirky thing about computer scientists, and there are many, is that we often start counting, or almost always start counting, with the number 0. And the reason that we start counting with the number of 0 is buried in the architecture of a machine. And later this semester we'll talk about why, in some programming languages, the 0th element is the first element. So that's one of the colorful quirks of computer science. There are many others. We draw our trees upside down, for example, with the roots at the top, but we'll get to that later. All right, so here's my specification of the stable marriage problem, and then the sort of intuitive version, no partner swap will improve the matching. But even this is not particularly precise, right? We need to operationalize the specification of the problem we're given. In particular, there's this messy word, prefer. I mean, match is a messy word, but we sort of get that, right? Match means take one from this set, and put them together. But what does prefer actually mean here? I didn't specify. So when you write your specification, you sometimes have to look at it and say, am I being really clear? And nowhere is this more apparent than writing a homework problem. When I'm writing a specification for me, I can gloss over things like prefer and say, oh, I know what that is. I know what I mean by prefer. But when I'm writing it for you, I have to be really careful that prefer is clear. This is one reason that we make Piazza available, because I write a lot of homework problems, and sometimes what's obvious to me is not obvious to you. So you get that homework problem, you open it up and read it, and it's not obvious to you. You go to Piazza and you say, what do you mean by prefer? So here's what I mean by prefer here. When I think about what the input to my problem is, I have the names of the n men and the names of the N woman, and each man gives me a list of all the women in preference order. So man number 1 says, I like woman number 1, woman number 2, woman number 3 in this order. Man number 2 says, I like woman number 3, woman number 2, woman number 1 in this order. It's really kind of high school, right? But that's the idea. At the same time, I get the names of the N women, and each one of them gives me a preference ordering on the N men. So woman number 1 says, I like man number 2, and then man number 1, and man number 3. So we're going to get a listing. So this clarifies, makes operational, or makes clear what the prefer means. So now we have an idea of what the problem is. Everybody sort of get what this problem is? Now we're thinking 5 men, 5 women, that's great. Think New York Public Schools, what was it, 70,000 kids, 50 schools, 100 schools, 200 schools, I forget. Think National Residency Matching Program. The input is the size of all the medical school graduates in the United States, Caribbean, and Europe who want to have residencies here. And the other size is the number of hospitals. So it can be quite large. And the output will be N pairings with each man and woman in a single pairing. So no man gets 2 women, no woman gets 2 men, everybody gets 1. So how do I do this? So as you think about this problem last time, anybody have any idea how you go about doing this? Go ahead.
Put a list together of things that they prefer in a partner, assign values to that list, create a score based on those values, and then look out like scores that are closest to each other of the people.
The scores of the 2 partners?
Yeah.
Okay, so what's your name?
Trevor?
So Trevor's suggestion is, correct me if I'm wrong, for every list, for every man's list and every woman's list, I'm going to assign a number to the person in the list. And I'm going to then look at all combinations of men's lists and women's lists and see how close some numeric combination of their respective scores are. So if Trevor ranks Nancy first, then maybe that's worth 10 points to Trevor. If Nancy matches Trevor first, that's maybe worth 10 points to Nancy, so 10 and 10 is 20. That makes a better score. Pick that one. It's a good suggestion. He's operationalizing the quality of the match as a numeric score. But what he hasn't told us is, how do I find the best matching? Implicit in his approach is that we look at all possible pairings and find the one where the cumulative score is highest. So what Trevor's solution does is helps us define the best match, but it doesn't tell us how to find it other than generating all the possible pairings. How many pairings are there of N men and N women? How many ways do I pair a man and a woman? Choose one. Something like N times N minus 1 over 2. It's about N squared. So for 5, I have to look at 25 possible matchings. For 170,000, I have to look at order of 100 billion. So you can see that's going to be slow. But, it's an approach. So, and good for raising your hand. Anybody else? How do you do it in the real world? You could date, right? We could do a dating thing. I'm going to suggest an algorithm. And what's going to be unusual about this algorithm is that it's not going to look like an algorithm. You've all seen the stuff in the newspaper about computer science and algorithms, and they say, what's an algorithm? It's a recipe. And they always have the example. You get a cake mix, you get some stick of butter, you get a cup of water, you mix them in a bowl, you beat them together, you put them in the cake pan, and then you cook it, right? You've all seen that example of the recipe. My recipe is not going to look like that. But it will be no less clear. So let me show you my algorithm. First of all, the input looks like this. For every woman, and there's the names, and every man, every woman ranks the men in preference order. And in this case, I kind of made random lists because I didn't know anything about these people, who was compatible or anything. I just made these up, right? But you can see that they're not the same, right? So Mimi and Maria have different utility functions. Mimi thinks pretty highly of Wesley, and Maria thinks he's a schmuck. So right away you see there's differential in who's picking whom. So this is my input. Is that clear? Everybody okay with that? And here's my algorithm. I'm going to choose a man at random, and I'm going to say to him, Wesley, propose to your first choice. So now, once he's proposed, if his first choice is free, meaning she's not engaged, then she has no choice but to accept. And she says, Wesley, you're on. We're engaged. On the other hand, if Wesley's first choice is previously engaged to somebody else, then she has a choice to make. She has to decide if Wesley is better than her current fiancé. How does she do that? She looks at her list. Is Wesley above, Schmuck on her list? Or if Wesley is less desirable than her current fiancé. So that's her decision point. If he is better than her current partner, she dumps her current partner, breaks the engagement. If, on the other hand, her current partner is better than Wesley, she rejects Wesley. Is that pretty clear so far? Yeah? A rejected suitor, if Wesley's turned down, he goes back into the pool of unmatched men. And, I got ahead of myself. A rejected suitor actually goes down his list and proposes to the next woman on his list. So Wesley's rejected by whoever. He says he crosses her off her list and he goes down one to the next one and proposes. Doesn't have to wait, just goes right ahead and proposes again. The suitor who is dumped, in other words, Wesley proposes to his first choice, she's engaged to somebody else and she dumps him, that suitor goes back into the pool to wait for another turn. So at every point in time, there's a man proposing or a woman deciding. And the pool of unmarried men or unpaired men gets smaller and smaller unless there's a rejection, in which case it gets bigger. We keep going until there's no unmatched men in the pool. That's it. That's the algorithm. Let's think about it for a minute. First of all, how do I know this will always end, always terminate? Trevor. There's a finite number of combinations, and every man proposes to a woman exactly once at most. Right? Because once he's rejected by her, if he's lucky, she'll accept, she'll get engaged, and it stays that way. But if she rejects him, he never proposes to her again because he goes on to the next one in the list. Right? And eventually, because every man has ranked every woman, eventually that man will go far enough down his list that he'll find somebody who's willing to take him. Now, this is a little weird. Again, colorful problem names and everything. The same algorithm applies if you exchange the word man for woman everywhere. In other words, it can be the woman who proposes and the man who rejects or gets engaged. Doesn't matter. One side proposes or the other side proposes. So let's see how this works. Here's my pool of unmarried men at the bottom. I'm going to pick one at random. It's James. I'm going to say, James, propose to your first choice. His first choice is Maria. He proposes to Maria. Maria, she's not all that crazy about James, but remember the rule. She is not engaged. And because the objective here is to get a complete matching where everybody is matched, she does not have the ability to say, James is not even good enough. I'd rather be a spinster. She can't do that. So everybody accepts. So we've got a match. James is engaged to Maria. Maria is engaged to James. Pick another person from the pool. It's Roger. His first choice is Mimi. He proposes to Mimi. She is not engaged. So Mimi has no choice but to accept. She's not that crazy about Roger. But she knows one thing. Roger is better than Tony. So she will never, ever, she knows at this point, she doesn't know if she's going to marry Roger or not. She's engaged to him. She's not married yet. But she does know with certainty that she will never have to marry Tony. Why? Because if you think about how these rules for proposing and engaging work, a woman's lot she's moving up her list. Because when she's engaged to Roger, she will only accept an engagement that improves her circumstance based on her preference ordering. So she will constantly be moving up her list. What about the men? Well, we'll see in a second. So we have 2 engagements. Next one is Tony. He proposes to his first choice, who's Maria. And boy, Maria is already engaged to James. So she checks out. There's James, and there's Tony. And Tony is a definite improvement. As you can tell here, Tony is a definite improvement over James. So what does she do? Well, she rejects James, accepts the engagement to Tony, and now, like Mimi and Tony, Maria knows that she not only doesn't have to marry James, but she'll never accept an engagement proposal from Wesley, so she's going to get Tony, end up with Tony or something better. Now you'll notice James over here, who just got dumped. Sorry, James, but here's what's going on. James, you know that Maria was engaged to you, but now she's dumped you. She will never accept you again. There's no reason for you to even bother proposing, because the reason she dumped you is because she's got somebody better. And that somebody better is not going away, so just cross her off the list. So just like a woman's lot here in this process always improves, the men's always degrades. Right? Your first engagement is always going to be with the best person available in your preference scheme. And it's only downhill from there. It's kind of like aging, right? It's only downhill. So let's see what happens. So James now, you'll notice, is no longer matched like Roger and Tony, so he's back in the pool. Pick another man at random. In this case, it's Wesley. Wesley proposes to Buttercup. Buttercup was previously, previously unengaged, right? Yeah, so proposes to Buttercup, who was not engaged. She accepts Wesley, who is her second choice, and James, Nick, and Tony are off her list. Now I pick Nick. Nick proposes to his first choice, who's Mimi. Mimi looks at Nick on her list, and he's a step above Roger, actually 2 steps. So she accepts Nick, crosses off James and Roger, and rejecting Roger at the same time, who returns to the pool. Okay? Pick the next one at random. I pick Roger. He proposes to his second choice, who is Buttercup. She sees Roger as an improvement over Wesley. It's a sharper dresser. And so she rejects Wesley, who returns to the pool and crosses Buttercup off his list. And she matches with Roger. So now I have Wesley and James in the pool still, because they're the only ones that are unmatched. They don't have a little heart. So I'm going to pick Wesley at random. He will propose to Nora, who is not yet engaged. She's not thrilled about Wesley. He's kind of middle of the road. But she has to accept him, so she gets engaged to Wesley, crosses Roger and James off her list. Finally, we pick Roger, who tries with Buttercup, who says no. He tries with Nora, who says no. He tries with Lily, who is unengaged, and so she says yes. And we have our last match. Okay? Now, I have 5 pairings, and I had to do a number of proposals and rejections, right? How many did I do at most? Well, at most, every man proposes to every woman. At most. Right? Think of this sort of in the worst possible case. The guy's first choice is always the woman's last choice. Right? And I pick men at random in exactly the right order to make the worst case happen. So there's a whole lot of shuffling going on. In that case, at most, every man will propose to every woman. In the worst case, that's 5 times 5, or 5 squared, 25 proposals. Now we had significantly fewer proposals than that. In the best case, every man proposes to his first choice, she's thrilled with the match, and you're done in 5 proposals. It all depends on the sort of the scheme of these orderings, which Trevor was trying to capture with a number. Here you'll notice that the orderings are never fully revealed. In the case, for example, of Tony, Mimi, Buttercup, Lily, and Nora have no idea where they rank on Tony's list. Because he asked Maria, she said yes, he's done. So we don't have to look at all the pairings because only the pairings that matter emerge in the algorithm. The algorithm will always terminate. And then the next question is, how do I know that this marriage, this pattern of marriages, is stable? So remember, stability is that there's no switch. So let's think about that for a second and walk through it, and then we'll talk about it again. So let's go on. So we know the algorithm is carefully described. It's not exactly a recipe because it's not this kind of linear sequential thing. Instead, the algorithm is sort of a collection of rules. Do this, and if you're in this condition, do that. But it's all pretty carefully described with these 4 actions. You're either proposing, you're either rejecting, accepting, or dumping. And you keep doing these 4 things in some order that is emergent from the rules I gave you until there's no more to do, and then you're done. So I claim that the algorithm is carefully described and completely described. And with this algorithmic specification, it should be little trouble for a programmer to sit down and implement exactly this system, this scheme, right? Those of you who've written code before, you could probably sit down and do this. Secondly, we know is that the algorithm always terminates because every participant ranks every other participant. All men rank all women. And eventually, every guy is going to find somebody who's willing to take him. Not true in the real world, but in our stable marriage problem, it is. In the worst case, every man proposes to every woman, as we just talked about. In the worst case, we have n times n proposals. That's the maximum bound. So we say that this problem, this algorithm, runs in computing time proportional to the size of the input squared, where the size of the inputs is that number n, which tells me how many men and women there are. Now, here's the interesting step. We don't want any swap to be better. So what would it take for the swap to be better? It would mean that some man who's matched to some woman would prefer another woman. Well, there's plenty of those, right? James had a lot of preferences. He went down his list pretty far. So it's no secret that James might prefer somebody else. But it also requires that the woman James prefers him to her actual match. And we know that can't happen. Why? Because when James finally proposes down the list to some woman, it's because every other woman in front of her has already rejected him. And the only reason that woman has rejected him is because she's engaged to somebody better. And in the interim, her engagement status can only have improved as she accepted better and better suitors. So the fact that the woman's lot increases on her list and the man's goes down is sufficient to guarantee that whatever match I get is stable. That's the specification I wanted. And I'm arguing that it meets that specification very informally, kind of waving my hands up here. Women get better, men get worse, can't happen. There are, however, ways to formalize that statement into what looks like a mathematical proof. So I can prove a property of my algorithm that says my algorithm produces a stable matching, which is what was asked for, and that makes my algorithm correct. Does everybody sort of get this? You know, it seems like a lot of extra stuff. Just sit down and write the code and make it work, right? How many engineering students here? A bunch of you, right? You're probably thinking, what the hell is he doing? He could write this code in 30 minutes. It turns out to be 4 or 5 hours later, but, Hope springs eternal. 30 minutes, I'm done with this. But you'll never really know if it's completely correct unless you can make an argument about this. I believe, this is sort of a digression, philosophical digression. The thing that differentiates computer science from engineers, you know, we're in a College of Liberal Arts and Sciences because our historical bloodlines are in math, not in engineering. That doesn't mean that some computer scientists aren't engineers. I don't have a computer science degree. I have a music degree and a bunch of engineering degrees, electrical engineering. I don't have a CS degree. But the mentality is different. And when I say I want to teach you to think like a computer scientist, I want you engineers, I have great respect for engineering because that's what I studied. I would like you to sort of leave your focus on building something that works quickly and think more about building something that's completely and absolutely correct. Because there is a difference. And if you can accept that difference, sometimes, look, sometimes a computer scientist, you'll give them a problem, they say, write a problem that computes final grades for this class. And I'll sit down, I'll say, oh, I can do that. Now what about the corner case where this happens or that happens, or I change the number of quizzes I drop, or somebody's out for COVID for 3 weeks? How can I build the absolute fabulous, perfect grading program that handles every possible case? Sometimes I really think that way, and then I run it once. In situations like that, just get the damn thing to work and be done with it. But if you're writing code that's going to run for years, if you're writing Microsoft Word, you don't want to have bugs that are introduced because you didn't reason carefully about how long it would run and what the inputs could be and whether it'll terminate and so on and so forth. So it's a different mentality that you bring to solving problems. I hope that that's aside for the engineering students, that's what I'm hoping that you take away from this. All right, one last thing. You run the algorithm with women proposing, you'll get a different solution, but it'll be stable as well. You can run the algorithm again with a different man ordering, selection ordering. You may get a different solution, but it'll also be stable. Speaking of which, let's look for a minute at the solution we did get. Who do you think did better on this market? Men or women in general? Let's see, we got 2 second choices, 2 first choices, and a 4th choice for the men. A woman, we have 1 first choice, 1 second choice, 1 first choice, 2 second choices, and 2 fourth choices. I think it's pretty clear the men had an edge here, right? Because they were doing the proposing. Now maybe if I'd started in a different order, I might get a different matching. But it's in general, I could prove that the proposer has a slight edge. Which is why sometimes running it with women proposing, you can see what kind of matching they get, and you'll see that they would have a slight edge. And it's kind of interesting because, and this may be on a slide later, I'm getting ahead of myself, but this is the algorithm that was used to match residents to hospitals in the National Residency Matching Program. It's slightly different because there, every resident gets matched to one hospital, but hospitals get a chunk of residents, right? So for your cardiology program, you may have 8 cardiology residents coming. So it's like a one-to-many matching, but the algorithm can be modified to do that. In the 70s, a more mathematically inclined resident noticed that the hospitals which were, in this sense, doing the proposing had a slight edge. So they sued him. And the result of the lawsuit was that the algorithm had to be changed. The change is simple. The residents became the proposers, so that that slight edge went to the residents and not to the hospitals. So sometimes these algorithmic details really matter. And this is the other thing, the other part about, I was talking to the engineers before, the other reason that thinking about your solution really, really carefully and spending that extra time matters is because sometimes there are repercussions, there are fairness issues or bias issues that are embedded in your algorithm that you can't see. Who would have thought, when I described the marriage algorithm, did any of you say right away, oh, that's enormously unfair to women? Well, a few of you did. Good for you. Usually nobody does and says, yeah, okay. Well, and I told you could have women propose, but the fairness issue is here that men tend to end up with better matches. And that's an implicit bias in the algorithm. There is a growing movement in computer science that you may have read about in the paper about algorithmic fairness and algorithmic biases. For example, in image processing algorithms or facial recognition algorithms that have been trained on predominantly Caucasian faces and don't do as well recognizing faces of, Southeast Asians or African Americans or Africans because the only thing they've really been trained to recognize are white faces. It's not something that people, sort of think about ahead of time, but these emerging biases are things that you have to reason about after the fact. And tell you a story from my own work. Years ago, I started working on a project that, anybody know what a diabetic foot ulcer is? Anyway, so diabetics tend to lose blood flow to their extremities. And so they will often get an ulcer on the sole of their feet, which basically is the leading cause of amputation in the United States. People amputate below the knee. And these ulcers don't heal because there's limited blood flow. Moreover, sometimes, these are elderly people. Looking at the bottom of your foot as you get older is harder. So we came up with a system where, using a selfie stick, they would take a picture with their cell phone at the bottom of their feet, and would come into our servers. We built a machine learning system that would examine the foot for the beginnings of an ulcer. Or it would examine and size an existing ulcer to see if it's getting better or getting worse. Because if it is, you can send a nurse or a technician to the house to debride the ulcer and dress it so that it has a chance to heal and presumably save that foot from amputation later on. Well, what a great idea. So we did this study. We collected a bunch of foot ulcer pictures. I can't look at them. It's the most disgusting thing in the world. You see bone and stuff, and I'm really squeamish, so it's not for me. But some poor graduate student working for me had to look at all those pictures and label them and mark the ulcer and so on. Turns out that, guess what? The population here is a very small number of minorities. So while diabetes is common in minority populations, we don't have any in our set. So we had to go to another hospital in Chicago to collect foot ulcer pictures from African American patients because the image recognition problem is different. This is not something we thought about beforehand, right? It became really apparent after the fact, but at the time it was like, oh yeah, we'll collect a bunch of pictures at the hospital and we're off to the races. So thinking before you code and thinking about what the problem you're solving is and thinking about what makes your algorithm successful, those are all things that have to happen first. You might not get it right, but at least you'll be open to doing better. Okay, so I'm off the soapbox. So notice that we've done a lot on this problem except write code. We've convinced ourselves that it will always terminate and will give us an output that matches what we want, a complete matching of men and women without swaps. And a better analysis might actually ask not how long does the algorithm take in the worst case, but on average, how long does it take? Because we'd find out that on average, we're not asking n-squared proposals. We're doing many fewer. It might be nice to characterize that. Then finally, when I implement this, the only question I need to answer is whether my program is faithful to the algorithm I've just reasoned about. So here's our picture again. And the issue here is that being a good program is important, but that just covers this step, taking the algorithm and producing the code. And computer science actually covers all of these steps, starting from the design process, which is the fun part. This is really the heart of what we do, and it's the fun part. all the way down to building and devising interesting and fabulously complicated tools that can take a program and produce efficient machine code in the best possible way, for example, or devising operating systems that can manage the running of machine code on the device that's used for many other things. Those are fascinating and complicated technical problems. Things like making sure that you can't put something in your program that makes the machine blow up. Stuff like that is really interesting. The actual coding part, it's not that interesting. But it's essential that you know how to do it well. So the point of this class is, we're going to talk about all of this, although predominantly this part. And mostly we're going to try to teach you to do this. But this isn't really the point. The point is to think about all of this and get a sense for because this is what you're going to do in the rest of your CS classes. You'll be taking, data structures, more programming, take a whole class on design analysis of algorithms. You'll take operating systems and networking and compilers, they're all down here. So you'll be learning up and down this whole spectrum. But in this class, it will seem like this is the only thing CS is, and that's wrong. Okay, questions? We leave that behind? Have we beaten it to death? You guys are like, you awake still? My daughters say that I'm the world's most boring person. And they may be right. But, you're stuck with me, so you got to make the best of it. At least it's bright and early, so we get it over quickly. Okay, why do we teach Python and not Fortran or C++ or Pascal? And the answer is it doesn't really matter. As a computer scientist, you're going to write in many different languages. You're going to take classes with us where you go in the first day and you say, and all the homework will be done in, Guru or some language you've never heard of. You say, wait, how do I write in Guru? And they say, you'll pick it up. The whole point is that these languages aren't all that different from each other. They share a lot more than what they don't share. The ideas and the constructs are similar. The syntax may not be. So we're going to pick a language, and the language we picked is Python. And the reason we picked Python is first because it's nice and interactive. Interactive languages are easier to work with, especially for beginners. It's type flexible, it's untyped. More about that later. It's got a bunch of useful built-in types. Lists, dictionaries, strings. You don't have to implement that stuff. If we taught this class in C, your first assignment would be implement linked lists. In Python, it's write a card game. So there are reasons that Python is useful. It's easier to debug in Python than some other languages, and there's lots of fabulous extensions to Python that somebody else has written. It's a great ecosystem for Python. But we really use Python because it's easy to learn, I think. It's portable, meaning you can run it on your phone, your laptop, your desktop, supercomputer. It runs on anything. It runs on my TV set. It's used in all over the web, and it's particularly been a fond choice of the data science community. So it's a good tool to learn. You'll find it'll be your go-to language for quick and dirty stuff. And that's why we use Python. We're going to be using Anaconda, the version Python 3.9. Lab 0 will tell you where to get it, how to load it on your machine. You probably should spend some time making sure you get that right, because you'll find that extremely useful. And we'll pick up here next time. Have a great weekend. We'll see you next week.